So structural analysis by simple structural surface method is the topic for this particular session. Uh, we're going to first define what is a simple structural surface. So particularly this particular method of performing structural analysis was first proposed by Mr. J. Pawlowski. So the reference that we have for this particular entire course is Vehicle Body Engineering by J. Pawlowski. And then later on, the same method has been used by many different designers and authors. So the another book or text or reference that we are using, An Introduction to Modern Vehicle Design by Julian Smith, also uses the same method. So like I told you earlier, both the books can be used as a reference for this course. And if you are not able to find Pawlowski, you might definitely find and use An Introduction to Modern Vehicle Design by Julian Happy Smith. So yeah, we go ahead with the definition. So a simple structural surface is a rigid in its own plane, but flexible out of plane. So this is how you define a simple structural surface. So this means that it can carry load in its plane. So both or different loads like tension, compression, shear, and bending. But whatever loads that are there, normal to the plane and bending out the plane are not possible. So it is not able to carry loads which are normal to that particular surface of the plane. And then using this particular definition, we will be analyzing all the different types of vehicles in different types of loading. So like we discussed earlier, we will see or we'll analyze a vehicle like a van and a saloon car under maybe bending or torsion, right? So I hope I'm clear. I'm going to go ahead. So if you want to analyze the structural performance using SSS method, this is what you need to know. The advantage of simple structural method is that your calculations are easy, not as complicated as FEM, but they are not as simple as beam method. But what is going to happen is that your results are going to be better than beam method, maybe slightly less accurate as compared to finite element method, but surely whatever results that you get using simple structural surface method, they are quite good enough, or you might compare them with the FEM method that you have. So maybe 10 to 15%, let us say, plus or minus or errors might be there, but you get a fair amount of idea if the surface that you're using is good enough to take up the load that the vehicle might undergo. Okay, so like I told you earlier, this method was developed by Pawlowski in the year 1964, and it determines the load in the main structural elements. So whatever different structural elements that you have for your vehicle, this method is going to help you find out the loads in those elements. So like discussed in the definition, a structural surface can carry loads in its plane. So these might be either tension, compression, shear, or bending. And overall, the surfaces are good enough to carry these loads. But whenever you have got any load which is going to be normal, so loads which are normal to the plane and are going to bend out, they are invalid and they are not allowed. So that is one of the conditions that you have whenever you want to have, or whenever you want to analyze your vehicle for structural performance using this simple structural surface method. Okay. Yeah. So the next part is analysis of a simple van for torsion case. So whenever the van is being subjected to torsion, using simple structural surface method, we have to analyze this particular van. And in the last session that we have to analyze a saloon car using simple structural surface method for bending. So these are the two parts or two different types of loading situations which we are going to be studying in detail. So, right. So to start with, in this particular case of analysis of a simple van which is under torsional load, we're going to consider 10 structural components. So I'm just going to count all these 10 structural components. So you start with component number 1. So the component number 1 can be seen in this particular diagram. Okay, so I guess fine. I'll just find out component number 1 a bit later. We'll start with component number 2. So component number 2 is this particular surface that you have, right? So this surface is going to be nothing but your front axle, and then component number 3 is shown over here, the rear axle. You've got component number 4, which is shown over here. Let us say this is going to be the place or the opening from where you're going to have air intake for your engine, right? After 4, component number 5 is the rear panel. Then you have got component number 6, which is the left side panel for your van. Component number 7, which is the right side panel for your van. Then you have got the component number 8, which is the floor of your vehicle body. Finally, you have got component number 9, which is the windscreen. Going on, component number 10, which is the roof of your vehicle body. So I believe from component number 2 till component number 10 we have covered. I am yet to find what is the component number 1. So once I understand or find it out, I will just let you all know. In the meantime, we are going to continue. So this geometry, that is what you see in front of you, is known as axle loads are known, or in this particular case, you know what are the loads on the axle. Edge loads are to be determined. Okay, so edge loads that you see over here, they have to be determined. So all these loads, what you see over here, these are edge loads. Okay. So in the case where you have, so again, by moment of balance R dash R, you are able to determine what is the overall forces, equilibrium forces. So you can see the equation that you have over here. So RR dash or R dash R upon 2 into TR is equal to RF upon 2 into TF. So this is the equation. I'll just repeat the equation. R dash R upon 2 into TR is equal to RR or RF upon 2 multiplied by TF. Okay. So TR and TF are shown in this diagram over here. I believe it is not, or it won't be visible to you because maybe you're logging in using your mobiles. So this is the way you're going to solve this entire assembly. And once you have written the equations for each of the simple structural surface separately, you're going to have some 10 different equations. Using those 10 different equations, you're going to solve for the load that is not known to you. Okay, so I'm going to now stop at this particular